Okay, thank you, Adriano, for the introduction and also for the opportunity to discuss this topic in the Expo Dubai. I will continue on some of the topics that were presented already by Dr. Eduardo, but I will have a stronger focus on Antofagasta, where I live, which is in the north of Chile. This is actually my city, Antofagasta, and the first impression you can have from this photograph is that it is not really very convenient for astronomy because of the many clouds you can see above the city. But if you move to the east, you will soon find the fantastic desert landscape of the Atacama Desert. And particularly at night, you will find the beautiful skies of the Atacama Desert that make astronomy possible at the worldwide top quality offered by Chile. One exercise we commonly do when talking about the quality of the Chilean sky is to observe Chile from space. Because if you can see the ground from space, it also means that you will be easily have access to observe the space from the ground. I'm talking from here. This is the location of Antofagasta. And I use this feature to quickly identify the Antofagasta region because it's a clear geographical landmark. And it's called the Peninsula of Mejillones. You can see that the Peninsula of Mejillones is easily knowledgeable in other pictures here and here. Yeah. Just to give you an idea that any image from space where you can see the Chilean north is not just a lucky image, but is an image that really presents what is a steady situation of clear skies that allow us to see the space from the ground. Now, this has given place to this situation in the north of the country, in which we can see a concentration of telescopes in two regions. The oldest classical one is the region of Coquimbo, where the oldest modern observatories were set up. And here, with the north to the right of the picture, the Antofagasta region, from where I'm talking, where some of the most recent and modern projects are being installed in this during the last decades. If we go back to a bit of the history of the largest telescopes in the world, we can see that in the 1970s the situation was a bit different. In the 1970s, the largest telescopes in the world were just 4-meter diameter size, and were mostly concentrated in the northern hemisphere, although some of those were in the southern hemisphere in Chile, in this region of Coquimbo, particularly the observatories of La Silla and Tololo. But if we move the picture forward about 20 years, we find that then the largest telescopes are 8-meter diameter. They are gradually shifting to the south, to the southern hemisphere, and concentrating in Chile. And this is the decade where Cerro Paranal and the region of Antofagasta in particular enters the scene in 1988 with the construction of the Very Large Telescope, the VLT, which was the largest telescope in the world back then, and is still the most advanced optical infrared telescope in the world. And what is very exciting about the times where we live is that we are now eagerly awaiting the construction of the new generation of mega telescopes, which are going to be up to 14 meters diameter. And of those mega telescopes, which we're expecting just 3 to be built in the whole planet, 2 of those are going to be set up in Chile. One of the one in the northern hemisphere is going to be built in Hawaii, the TMT, the 30-meter telescope. But in the southern hemisphere, 2 are going to be in Chile, the Yaya Magellan telescope in the region of Atacama, and the extremely large telescope in the region of Antofagasta. And we are expecting this in 2027, and it's again going to be the largest and most advanced optical infrared telescope in the world, to which some other important telescopes worldwide should be added, such as ALMA, which is the largest ray observatory worldwide, considering its interferometric capabilities. Now, having gone through this short summary of the situation in Antofagasta in particular, I need to add one small telescope, which is going to play an important role in what follows. And this telescope is built by the Universidad de Antofagasta, where I work. And it's actually the first Chilean state-owned observatory under the sky of the Atacama Desert. It was opened in 2015. It already has 60-centimeter telescopes and some other smaller telescopes. And we are waiting for COVID-19 to give us a break to set up a second dome, because we have some funding supporting the continuous development of the observatory. So I'm going to go back to some important role of Koirama in the analysis of the effects of LEOsats on astronomy in a moment. If we observe now the geographical distribution of the telescopes in the Antofagasta region, which I'm using, as you can see, as perhaps the main test case of the effect of light pollution on astronomy, but we should not forget that this is important for the whole north of the country. We can see that the telescopes are concentrated in three main areas. One is very close to the sea, where ESO's BLT and ELT are located. Now there's some sort of middle part where Universidad of Antofagasta's Koirama Observatory is located. And then closer to the mountains, we find the Atacama Astronomical Park, and also ALMA and some other projects. If we make now a comparison of this geographical distribution with what is the current state of light pollution in the region, we find this situation. In 1997, there was a global study of light pollution based on satellite imagery, which revealed that light pollution was indeed a concern, mostly as contribution from cities and mining companies. But you can see that the position of the observatories is more or less safe back then. These are again the three areas I talk about, and they look protected from the effect of light pollution. But if we're analyzing this problem, we should not focus on just a single picture but on a trend, and on what's happening with the trend if we compare this picture with the same picture some years later. And this is a bit alarming that in 2006, now we see some new sources popping up on the ground and getting closer to the observatories. And now in 2014, the situation is a bit more alarming, although admittedly the sites of the main observatories is still safe. But if we look at the trend, of course the trend is concerning for us. So we're trying to react, and we have been trying to strengthen the law. That has been one of the recent efforts in the country to give a stronger protection to the Chilean skies in front of the threat of light pollution. But also we have been trying to be innovative in the approaches to deal with light pollution. So one of the things we have been doing is that we're trying to test new approaches to measure light pollution on the ground by means of drones. And this is actually a project that was funded last year, and it runs until 2023, that aims to study light pollution sources on the ground by applying the same photometrical techniques we apply when observing the skies, but to the images acquired by means of a drone. So basically, we are reversing the problem of observing the sky to observe the ground, consider light pollution sources as a sort of star, and then using this approach to the problem, we're going to try to isolate the sources that will be in violation of the Chilean regulations. This will provide an automatic means of identifying infractors to the law, which is going to be a useful service for the Chilean authorities. And the Koirama Observatory is going to play a role of being a testbed for calibrating light pollution sources, because you can imagine that in contrast to what happens when we observe the sky, in which we have some standard sources of calibration given by some stars we know very well, on the ground the situation is a bit different. So we need some artificial standard source that we are going to set up in the Koirama Observatory to calibrate all of this. But again, and there's going to be a talk by Marcos Diaz in this series, and I know he's going to talk more about this project. We have also been trying to address the same problem, but using images from space, but from a new satellite that's being designed with the specific purpose of measuring the effect of light pollution. One problem we have with the current satellite data is that they are acquired by satellites which are not specific for the purpose of measuring light pollution, so they may not be sensitive in some portions of the electromagnetic spectrum which are of particular interest for astronomers. So we are trying to solve this by designing our own satellite, putting it into orbit, and then observing the data, analyzing it from in a collaboration of Chilean universities, and again use the Koirama Observatory as the artificial standard source by which all the data is going to be calibrated. Now, a side effect of this, a side product, a byproduct of this project is that we're going to be able to run communication experiments with the satellites. So this might be of interest for the industry and beyond the characterization of the light pollution coming from the devices. Now, while we were very concerned about the light pollution coming from ground sources, some years ago, in 2019, we started receiving reports about the strings of pairs being observed by citizens, not just professional astronomers, but by many people concerned about what was happening in the sky, that later on we realized were produced by mega constellations of communication satellites that were being put into orbit by some private communication companies such as SpaceX. Their constellation of satellites is called Starlink, but it's not the only one. There's the case of OneWeb that is also sending satellites for the same purpose this year. And the general public and the international professional astronomical community became very interested in the problem after some concerning images were released illustrating the effect on astronomical images, such as this one, which was produced by the DECAM instrument in Cerro Tololo on November 18, 2019. And you can see that there are many white streaks going through the image, which are basically overwriting the astronomical information. So it is information that basically you lose after a satellite is passing in front of your data. So if this was going to be a common occurrence, the threat to astronomy now as an additional source of light pollution coming from space is very clear and very alarming, in addition to what was our original concern of light pollution coming from the ground. In reaction to this, one key step has been the recent creation of the Chilean Low Earth Orbit Satellite group, which is called CLIOSAT. That is very recent in terms of being a group. the nationwide call was released just this month. But this mission is to assess the impact of LEOSat's mega constellation communication satellites on the night sky, and what effect they have on optical and radio astronomy. So on the effect on all the observatories who have been talking today in the talk by Eduardo Ibarra and my talk, both in optical, radio astronomy, infrared, etc. And also to coordinate the different efforts from Chilean groups in order to maximize the results we can achieve as a well-organized group and liaise with similar efforts from groups that are being organized abroad. As I told you, the group is very recent, but some of the actions are not. So we started a couple of years ago working on this problem. So this is basically a formalization of something which is already going on. So I will present some of the most interesting results from the actions of this group. And particularly, some key results were obtained in 2020 as the study of SpaceX Starlink modified satellites. When in 2019, the community was concerned by the effect of SpaceX Starlink satellites on astronomy, some conversation started with the SpaceX in order to modify the design of the satellites. Two experiments took place called DarkSat and VisorSat, which were modifications in one case to the coating of the antennas of the satellite, and in the other case, it was the deployment of a blind that will block the sunlight, so it will not reach the antenna in order to prevent reflecting the sunlight to the ground, which is basically what we detect as bright from the satellites. What we observed, and it was published in 2020, is that the DarkSat and also the VisorSat experiment are not really enough to control the problem. In particular, in the case of DarkSat, they reduced the brightness of their satellites, but only by a factor of 2, when at least a factor of 20 was required. So they were really far from the recommended reduction on brightness. And again, for VisorSat, we demonstrated the same. Here is the acceptable magnitude limit at an altitude of 550 kilometers. More bright, brighter is upwards in the image, and this is the limit brightness we can accept to correct the effect on astronomical images. And here are all the standards Starlink satellites. This is DarkSat, which is slightly less bright, and this is VisorSat, again, slightly less bright. But all of these, all their experiments, we demonstrated that they are not enough as a correction to the problem. Moreover, we also demonstrated in an article published in 2021 under the leadership of Jeremy Troyland-Reed, who is the leader of the CLIOSAT group in Universidad de Atacama, that beyond optical astronomy, the reduction of brightness is a lot less in infrared. And this is very important because we have some important sensors working on infrared, and their strategies, the strategies of SpaceX, are really not enough to correct the problem, but are even less effective on the infrared. They have been naturally more concerned about the effect on optical, because this is what people will commonly detect with the unaided eye. What happens with OneWeb, which is the other important player in the world beyond SpaceX? We ran observations with a telescope in Spain, in Calar Alto, and following the recommendations of 2 international meetings that took place in 2020, that produced an equation that allow us to compute the recommended maximum brightness for a satellite depending on the altitude of the satellite. We computed, but that for this case, the limit magnitude is 7.9, and our measurements indicated that the OneWeb satellites were 8.14, which being a higher number means that they are less bright. So in principle, this meant that they were in the safe zone. And we were happy to find that this would be a good news for the astronomical community, that this new generation of satellites by a different company were actually complying with the recommendations produced by the astronomical community. But we were not sure because these were just 2 observations of 2 satellites, but who knows what happens when you really run a statistics. So we started a project using the Danish telescope, which is operated in Isos La Silla, and that during 6 months every year is operated by the Danish community for exoplanets projects. But they are able to allocate time for some other parallel projects that use idle time, basically. And for the 2021 season, they accepted the observation of low Earth orbit satellites as one of the complementary projects in the run in the Danish telescope. Basically, this year we obtained 563 successful observations of both Starlink and OneWeb satellites. And given that these are numbers of importance, we can produce statistics, and also we can produce statistics using different portions of the electromagnetic spectrum and really assess what's going on with the effect of the satellites on different parts of what an astronomical telescope can detect. So this is our corrected result today, which is different from our preliminary result. And we can see that with this being the limit magnitude, to the left of the picture, we see that more or less 50% of their satellites are too bright. So unfortunately, the news are not so good. OneWeb has still a lot of work to do to correct the performance of their satellites to comply with the recommendations of the astronomical community. Finally, the CLIOSat project is also developing a global LEOSat observing network. So we're not just working with telescopes in Chile, we also consider telescopes well in Spain, in Vietnam, and in South Korea, but we are looking for more. So if people listen to this presentation and are interested in collaborating with us as part of this global observing network, please get in touch. And I will finish my presentation mentioning that, again, there's an opportunity here for not only use this effort to assess negative effects of LEOSats on astronomy, but also to provide some services to the industry. In particular, one of these possible services is the correction of TLE accuracy, as we are producing lots of data with astronomical precision, and we are able to continuously correct the TLEs using our astronomical, using our data acquired with astronomical standards, which we have seen introduces an important correction to published TLEs whenever we have used the information. So we think that this may be of interest for the industry, and that this may be then an opportunity to collaborate and have a positive channel of collaboration with the satellite industry as well. Okay, thank you very much once again for the opportunity to talk to you about the progress with these topics, and again for the organizers for providing this space. Thank you very much.